then was as a postdoc, a staff member at the Raspberry Lysource. Yeah, something like that. Till he joined National Taiwan University in 1998. He is now a distinguished professor in our department. His research area is in theoretic condensed matter physics, and he has been a very outstanding researcher. Received 3 times outstanding research award from National Science Council, and also is the recipient of the academic award from Ministry of Education. He is also a member, a fellow of the American Physical Society and British Physical Society. He has published many papers with very interesting results. And today he will talk about spin Hall effect. So let's welcome Professor Guo.
Thank you, Chairman. Also, thanks, Chairman, for the invitation to give a presentation here. So today I'm going to talk about spin Hall effect, which is quite an interesting topic in the past 10 years. Okay, so this will be the plan on my talk. In the first part, I will introduce to you what's the spin Hall effect and give a brief overview of the development on this topic in the past 10 years or so. And then what's next, basically tell you from my opinion what's the outlook for this field. And then in the next 2 sessions, I will present my own research result on this topic. First, I will briefly show you how can one calculate spin Hall effect using elegant Berry phase formalism and then apply to semiconductor and the metals. And then on the third part of my talk, I will show that this current hot topic can actually be related to a classical many-body problem in condensed matter physics, that's Kondo effect. And then we tackle this many-body Kondo problem using a quantum Monte Carlo calculation. And then finally, I'll give a summary. So first, what's the spin Hall effect? So let me begin with the ordinary Hall effect, which people in the audience learned in general physics or solid-state textbook. So when you have, say, a conductor look like that, and you apply an electric field, and in the meantime, you apply a perpendicular magnetic field. And then you take a voltmeter. You not only measure voltage longitudinally, and you can also measure the non-zero voltage. And that was the phenomena discovered by Erwin Hall when he was a PhD student in Johns Hopkins University. And so we call it Hall effect. But because of later development, this is called ordinary Hall effect, because we can understand this phenomenon simply by Lorentzian force in electromagnetism. Lorentzian force show that a moving charge will not go straight forward, will be deflect. For example, current flow this way, and the electron will be going that way, but instead it will be deflect to this edge. And if it's Hall carrier, and then will be deflect to this one, and in the equilibrium there will be positive charge accumulated on this side, and the negative charge accumulated on the other side. So there's equilibrium voltage build up, and that's called Hall voltage. About 2 years later, he also found that actually you can also observe this phenomena in a ferromagnetic conductor without a magnetic field. Okay, So you can also find voltage. But at that time, he could not understand the phenomena, so he called enormous Hall effect. Okay? But now, after special relativity was invented early last century, and also quantum mechanics, now we'll be able to understand, at least in the qualitative picture, how this enormous Hall effect occurred. Now, we know that in a ferromagnetic conductor, there are more electrons with a spin up than with a spin down. So, because of relativity spin orbit coupling, now electron moving in this conductor where this kind of diffraction to one side and to the other will depend on the spin of the electron. Okay. Now, for example, say if we have a conducting electron going this way, now electron with a spin up will be deflected to this side, and that's well-known phenomena due to spin orbit coupling. You can find that in molecular atomic physics it's called Mott scattering, in solid state called skew scattering. Okay, but electron with a spin down will deflect to that way. But because we have more electron going this way, so this side will be negatively charged, and then because charge neutrality, we have positively charged on this side. Then this gives rise to Hall voltage. Now, more than 90 years later, two Russian physicists realized that if we have a non-magnetic conductor, now this phenomenon is still there, but instead we have electron with a spin up going that way and the electron with a spin down going that way. So there is no charge current, but instead we have a spin current. You can see that electron with a spin up going that way, electron with a spin down going towards my side, and then we have a transverse spin current. And this is called spin Hall effect, discovered by two Russian physicists in early 70s. Now, because the type of spin Hall effect I'm going to tell next, and this was called extrinsic spin Hall effect because this was proposed due to impurity. Okay, so and the current interest in spin Hall effect was mainly due to this paper by Professor Nagaosa from Tokyo University and Zhang Shousheng from Stanford University. Okay, they study traditional semiconductor, 3-5 semiconductor. Okay, and this is the typical band structure of semiconductor. You can see that we have so-called hole band structure with a heavy hole and the light hole band structure. But they model this band structure using so-called Luttinger model. Okay, and then they realized that because the singular point at the gamma point, okay, and this singular point could mimic so-called Dirac monopole, but in momentum space. Okay, now then you can construct so-called gauge field, and then this gauge field will modify the electron or block electron velocity in solid, giving additional term here. Okay, now this term depends on the wave vector velocity, which is determined by the applied electric field. Now you plug this into this formula, you can clearly see that in addition to ordinary velocity we have already in the band structure, you have additional velocity which is perpendicular to the electric field. And this will give rise to so-called intrinsic spin Hall effect. You now plug it into transport theory, you get the spin current giving that look like that. And with the appropriate doping, you can actually find spin Hall conductivity which can be comparable to ordinary conductivity. And that's the so-called intrinsic spin Hall effect due to spin orbit coupling effect on the band structure. Okay. Now, in about the same time, a group in Austin, Chen Liu and Alan McDonald, they also realized that in ordinary 2D electron gas, if this will be the harmonic for free electron, but then you add spin orbit coupling term, which is called Rashba spin orbit coupling. Then the parabolic band structure will be splitted and look like that. Okay, this is the equal energy contour. Okay, you have two circles instead of one, and they are spin split, and the spin look like a chiral. Okay, so this is Rashba band structure. But then they realized that if you apply electric field, now because of spin orbit coupling, this applied electric field in effect apply a spin torque onto this electron. And then this originally moment, let me change the battery. Okay. Now, so when you, because of this torque, the spin originally in plane will now stick out for positive momentum, and the spin on the other side of this line, and spin will stick down. So, and then the electron will be also deflect this way, and the electron with spin down will be deflect that way. Effectively, we again have a transverse spin current. Okay. Now, these two papers stimulate very enormous interest in the field of condensed matter and the spintronic. Okay, I'll tell you why. Now, for nearly about 1 year, nearly 1,000 papers were generated. Okay, but there's no experimental paper was published. So people worry that this is going to die down because physics is an experimental science. Okay, although I'm a theoretician. Okay. Now, fortunately, people in Santa Barbara, David Echelon group, they finally published a paper in Science in 2004. They clearly demonstrated in semiconductor, they observe, or they apply a current, and they're using optical measure method to measure spin accumulation on both sides. And this is what they measured, and this color code spin up and spin down accumulation. You can see very beautifully, they clearly demonstrate this spin Hall effect in semiconductor sample. Okay, so say this will be spin up and this is spin down, and using circular polarized light to determine this. Okay, and they attribute this to so-called extrinsic spin Hall effect because it's independent of crystal orientation. Okay, and in about the same time, people in Hitachi lab in Cambridge, they also observed in spin Hall effect in p-type two-dimensional electron gas quantum wells. Okay, and this time they're using LED and again using optical method. Okay, not much later than that, and my colleague, Professor Chen Yongfang, also detect this in a very important semiconductor, so-called nitride semiconductor super lattice. Okay, again they're using a circular polarized light and to detect, and they by tuning the laser power, they will be able to demonstrate that this is kind of intrinsic spin Hall effect because laser power changes the strength and then changes the Rashba spin orbit coupling parameter, and the experimental result can be confirmed by theoretical calculation. Okay, now to be useful for spintronic, it's no good that you need an optical method to measure spin Hall effect. So people think about any way we can measure spin Hall effect electrically, and this is exactly what Tinkan in Harvard did. Okay, so they study. This is the cartoon picture about spin Hall effect. You can see that we have transverse spin current look like that. Now imagine that in a conductor with a spin orbit coupling, you inject spin current. Okay. Now because spin Hall effect electron with spin down will go in that way, and the electron moving along this direction with the spin. With both spin will go in that way. So there will be a negative charge accumulated on this side and a positive charge accumulated on this side. So you can now using ordinary voltmeter to measure Hall voltage, and this process is called inverse spin Hall effect. Okay, so Tinkan's group used this so-called inverse spin Hall effect, and then using on-Sark relation and be able to deduce spin Hall conductivity for aluminum, which is quite small, and also you need to do it at a very low temperature. But this experiment caused a lot of attention in Japan. Okay, so Sato is now very famous. First observed inverse spin Hall effect in platinum. Okay, and even at a room temperature, and so that's caused a lot of excitement. And then this followed by another paper by Tokyo Institute of Solid State Physics Otanis group. They now measure direct spin Hall effect again in platinum. Okay, and they found that even at room temperature, you have spin Hall conductivity about 2040 omega centimeter inverse. And so, this papers caused a lot of attention worldwide, and now hundreds of experiments has been carried out so far. And if you are interested, you can this can be found by recent review by Alex Hoffman from Argonne National Lab. Okay, so why people pay so much attention to spin Hall effect? Now, people in the audience heard a lot about the spintronic or 自旋电子学, okay, in the past 10 years. Now, to really realize spin current transport electronic, you need at least 3 elements. Okay, what's the 3 elements? One is that first you need to be able to generate spin current. Okay. Second, you need to know whether you have successfully generated spin current, i.e. current detection. Then third, of course, you need to manipulate spin current in order to make an electronic device, okay, or spintronic device. Now, traditionally, you can easily generate spin current by simply replace non-magnetic conduction lead by ferromagnetic lead. Okay, so electron coming out from ferromagnetic lead will automatically become spin polarized. But however, there are problems for this. If you want to build spintronic with the current semiconductor technology, for example, in Sinju, then it will be difficult to incorporate magnetic material or apply magnetic field. Okay. Now, if you use spin Hall effect, you use non-magnetic material, use electric field, you can generate pure spin current. Okay. So you can get rid of a possibility of using magnetic material or magnetic field. Okay. So and then this kind of material can be quite a good integrate with a conventional semiconductor technology. So that's one point why people are so amazed about discovery by Zhang Shoucheng and Alan McDonald and Chen Liu and so on. Okay. Now the second element for spintronic is how to detect spin current. As I showed you before, if you use inverse spin Hall effect, now you'll be able to detect spin current you generate in a solid. Okay. Now, it was demonstrated about more than 1 year ago in science. You can also use pure spin current, which does not consume electric power. Okay. You can use pure spin current by the mechanism so-called spin transfer torque. You can actually switch this micromagnet magnetization direction up and down. So that means you can read and write memory device using pure spin current. Okay, so all these are very exciting because you can imagine that now, as actually our chairman some time ago measured the electricity consumption in our building and found the PC cluster is actually occupy a big fraction of power consumption. So imagine that if you can use spin current, then you can save a lot of electricity, okay? So you can see that you can write memory using spin current. And that's why people are so excited about spin Hall effect. Now, not only that, sometime, a few days back, I talked to somebody from National Science Council, and he told me that 2/3 of our proposal in condensed matter have word like a topological insulet. Okay. Now I want to tell you, topological insulet coming from research on spin Hall effect. Okay, that's what I'm going to tell you. You know that I introduced ordinary Hall effect. Okay, then people after quantum mechanics was invented, people think whether we can have quantized Hall effect, and that's quantum Hall effect. You can see in this is the cartoon picture of how electron behavior under strong magnetic field. Most of electron we are doing just circle motion because of Lorentz force. However, by electron at the edge can move on, okay, and that gives rise to quantized conductance, and that's called quantum Hall effect. And if you look at the band structure, we have a bulk insulating band structure, but on top of that we have edge band. Okay. Now because we have only one edge band, and that gives rise to conductance of 1 unit. Okay. And this kind of conductance can be calculated using so-called Chern number. Okay. In terms of Bailey curvature. Okay. Now, so immediately after those paper was published in Science and Physical Relator, Charlie Kent from Penn State University, he was thinking, can we have quantized version of spin Hall effect? Okay. Then he realized that for graphene, another hot topic material, this will be graphene, and if you have a graphene ribbon, okay, with a so-called zigzag edge, and you get the band structure look like that. Okay. But then he realized that if you add to this graphene Hamiltonian Horden-like spin-orbit coupling, okay, then there we have a gap opening. In addition to the gap, you have this two edge band. Okay, that's the edge band. Okay, and this edge band is spin polarized, so that can give rise to spin polarized edge current. You can see that one going that way with spin up, and the one going down with the spin down. Okay. Now imagine that you apply electric field, so this edge current will be fully spin polarized. So this is the concept of quantum spin Hall effect. But this kind of model or system turned out to be the first topological insulet, because this is insulated, but the edge state is conducting. So that's the topological insulet early version. However, this gap opening is due to spin-orbit coupling. Graphene, we know that atomic number is very low, so spin-orbit coupling is very small. And so this lead Zhang Shaocheng's group to look for heavy element composed two-dimensional system. So they look at, again, semiconductor material. This is called inverse band structure semiconductor. Okay, this is well-known semiconductor for infrared detector, I remember. Okay, now they realized that if you tune this quantum well weight, so the system will go from trivial insulet to topological insulet. Okay, so you can see that the conductance will be 0, it's ordinary insulet. But then if you, by tuning the quantum well weight, and then you move on to non-trivial topological insulated phase. And this kind of proposal was published in Science, and then 1 year later was confirmed experimentally by Molenkamp using the same material. Okay, so you can see here that at least roughly you can see quantized conductance being reported. But more recently, Du Riley from Rice University also report that they observe this quantized conductance in other semiconductor material. So you can see that topological insulate was coming from the idea for in order to find a material which can support quantum spin Hall effect. Okay, but then later on, again, Charlie Ken, they think, how can we realize 3D topological insulate? So they, and then with a very bright PhD student Fu Liang, is now in Harvard, they be able to formulate very elegant theory where to search for three-dimensional topological insulate. Okay, now topological insulate, as I mentioned before, currently is a very interesting topic in physics. Now the reason is very simple. It can host a number of exotic phenomena, and for example, Majorana fermion superconductor, ASIAA electrodynamic, and the quantum enormous Hall effect. Okay. By the way, this is the quantum enormous Hall effect published by Beijing Tsinghua University Xie Qin's group. Okay. Professor Zhen Yang may make a remark. I remember when I was in Tsinghua that this is so-called Nobel Prize winning work. Okay. So now another topic was spin off or spin Hall effect is so-called spin electronic. Okay, this is a very new word. It was coined about 2 years ago. Okay, now what's a spin electronic? It's basically a spin electronic device driven by thermal rather than by electric. Okay, now I tell you how this can occur. I mentioned before that if you have a non-magnetic semiconductor, you apply electric field and then you generate transverse spin current. Now, instead of electric field, you can imagine you apply thermal gradient. Okay, say high temperature here and low temperature there. Then electron will also move. Now again, we have spin orbit coupling there. So we have transverse spin current, and this is so-called spin Nernst effect. People know Nernst effect, is it? So now this is spin Hall effect version of Nernst effect. So that's called spin Nernst effect. So you can see that you can also generate spin current by using temperature gradient. And another topic which also relates to spin Hall effect is spin Seebeck effect. I think in general physics experiment course, people do Seebeck experiment. Is it? What's Seebeck? Basically, that if you have a conductor, you apply a temperature gradient, then there will be a charge voltage across this conductor. But now, if you in a ferromagnetic material, okay, you apply a thermal gradient, then instead of charge voltage build up, you have spin accumulation with a different direction on different sides. Okay. Now, then you can measure this, or this kind of phenomenon is called spin Seebeck effect, and you can measure this kind of effect using platinum again. Okay. So platinum, you put the platinum here, but because spin current is going another way, and you get due to inverse spin Hall effect, you get the voltage which look like that, and then you put another platinum conductor here, and you measure the whole voltage again, and you find opposite side, and then this demonstrate that you can indeed have a spin Seebeck effect. Okay, so these two phenomena tell you that we can actually maybe using wasted heat, okay, to generate pure spin current and to try spintronic device. Okay, so that's the overview about the topic in the field. Now let me briefly present some of my own research. So I started this research in later 2003 because I met Chen Liu and some others. They say that people who are doing first principle calculation should enter this field because there are a lot of calculation needs to be done there. Okay. Now, so let me first tell you our motivation. In that